Welcome back to another episode of Scientifically Simple. We are going to be building off of some of our previous videos where we focus on the actual reaction and calculating the equilibrium of that process. In today's video, we're going to be discussing those fundamentals focused around steam methane reforming, a topic that we've discussed previously. See the video in the link below for future reference. Mo?
Thank you, Brandon. So before we start today, I would like to provide a special thanks to Taylor Archer and Clariant for his input regarding the material that we are about to be presenting today for the steam methane reforming. So as a recap, we're going to be like this, have a recap around the laws of thermodynamics that we have discussed previously. And we're gonna have like a brief discussion about like how to be determining an independent set of reactions when we are dealing with like a big sum of various reactions that's including dependent and independent versions. And then after that we move from there to the thermodynamics and the steam methane reform of the steam methane reforming. So we have established before that a state function is a path independent, while path function is a path dependent. Enthalpy, internal energy, and entropy are definitely state functions. Pressure, temperature, volume are interdependent, specifying two. The third can be determined. And calorimetry and heat reaction deduction. And along with that, we spoke about the how specific heat was derived and how it relates to the specific heat at constant volume. Last but not least, the thermodynamics integration of the chemistry led to a revolution in the chemical industry, as we have seen in previous episodes, starting from First World War. So we talked previously on first law of thermodynamics and its application to energy balance, and we have established because enthalpy is a state function, it doesn't matter how I go from point A to point B. And from there we basically came to the conclusion of how to get to the adiabatic flame temperature. So that was established pretty much like going from just pure physical laws of thermodynamics to start including the chemical reaction as part of the overall thermodynamic laws. Now going to the steam methane reforming chemical equilibrium, and I just like showing there on the top right, if like our audiences did not get the chance to see before the two episodes we spoke about regarding hydrogen synthesis, as an introduction, and then a special case of the steam methane reforming, it will be great for them to be like watching those as well, because this episode is going to be an extension of that.
Right.
So just like a small shortcut for linear algebra, I'm not going to try to be going too much details in that sense, but normally, like if we are dealing with chemical reactions in a specific problem, it's essential to make sure that the chemical reaction that will matter for us in our analysis, whether it's in the thermodynamic analysis or even in the kinetics analysis, is that we deal with the independent set of the chemical reactions, which means that's a lot of simplification and basically removes any unnecessary complicated mathematics in there. And from thermodynamic perspective, that basically makes our life easier as well. So there is something called that matrix rank, and basically if I have a given matrix like A, what it shows is that this matrix has a rank 4, which means I have like 4 you know, 4 rows,
Right.
and 4 rows pretty much with that like diagonal kind of a matrix. Anything below that rows, for example, this row and this row, that's an independence. This is a sign of dependence, and that's what we call nullity of matrix A, which basically that's how many dependent variables are there. There are always, of course, like the rank of the matrix has to be like either n or less. Like it can, like, you know, you can't have more independent reactions than what the matrix is having as a rank, which means, like, you know, that's going to be like over-defined problem. So case 1 is basically the number of variables linearly dependent, aka defined. The case 2 rank is basically the number of variables under determined problem. The case number 3 is the number of variables over determined problem. So these
for those of us back home who are like really rusty in math, what you're saying is each row represents one specific reaction, correct?
Exactly, but like it's going to be leading to that because we're gonna do an operation. Again,
Okay.
That operation doesn't necessarily has to be done by hand. It can be done by Mathematica, it can be done by Maple. But eventually, after you do something called, I need to get my matrix to be in the row reduced echelon, that means eventually it's going to go down to a diagonal matrix like that. If that diagonal matrix end up like basically being only this, that means you pretty much all your actions are independent. If like
Completely
you end up like
Yep,
exactly. Like pretty much what it does is saying, like in a very like simplistic way, you can't do any algebraic equations on any of these chemical reactions to reproduce the other chemical reaction.
Okay. All right.
And that's the whole essence of there. But of course, like if you are dealing with one reaction, it's simple. If you are dealing with like 3 reactions, it's simple. But if you are really dealing with a whole gigantic, like, I don't know, 10 plus reactions, it will be like the most abstract way of trying to be avoiding any complications.
Right.
Is basically to do the simple operations.
Right.
And we're going to be like going to the discussion there. So, for example, let's say I have a matrix like A given in this form.
Right.
In this form, you know, if we go back to linear algebra 101, and basically I'm going to make an operation that will take place in row number 3, and that operations I'm going to be like adding row 3 to row 1. So when I add like row 3 to row 1, there's going to be 0. -5 and -2 is going to be -7. -1 and 0 is going to be -1. 8 and 4 is going to be 12. And then after I do that, you know, I will go to, I'm going to make a mathematical operation in row number 2. That's going to look like, you know, row 2 minus 3 row 1. Simultaneously, I will do operation in row 3 as a form of row 3 plus row 2. You eventually end up in this form. So what you actually can deduce from this is that you only have two independent systems. Like you were already completely eliminated the third raw. And that is what we mean. Basically what you had here is like, you know, these are two, like the rank of that matrix is going to be 2. And basically, you know, it's going to be a neutrality of like matrix A is 1. So away from the abstract mathematics, we are going to be taking this into the chemical reactions. So in steam reforming reactions, someone can be like writing these. Yeah, I mean, this is what eventually like the linear algebra we want to be like utilizing in chemical engineering without it like, you know, because like there's a purpose behind it. But like the steam method in reforming, for example, it can be written in those, like, let's say you are writing 4 different reactions, like methane and carbon dioxide, which is the dry reforming, gives you like carbon monoxide and hydrogen, carbon monoxide and water, give you like carbon dioxide and hydrogen, which is a CO conversion or water gas shift.
Yep.
Then you have like the two reactions that we observe in steam methane reforming. Methane was water to give you either carbon monoxide and hydrogen or carbon dioxide and hydrogen. So the matrix A that we spoke about earlier is going to be representing the stoichiometric coefficients that we have here. So for example, like in this equation here, you have methane, carbon dioxide, carbon monoxide, hydrogen, and water. These are the components that you have. In first equation, it's -1 because it's a reactant. Carbon dioxide is -1 because it's a reactant. Then it's 2 and 2 for hydrogen and carbon monoxide, and then 0. There is no steam. And you go down here and basically you fill each row with the stoichiometric coefficient of the reaction that
you
we
wrote
have.
out. Right.
Basically.
Right.
And then what you be doing there is basically you're trying to be getting the reduced form of that. And in a simple matter, when you do this, like we have discussed earlier, here is your operation, and you do row transformation, you end up like finding that two reactions that we have are dependent. And basically what we need to deal with from now on is just like two reactions in our thermodynamic analysis or even in our kinetics. So based on what we have earlier, this means the null is a 2 and our matrix rank is a 2, and we only have two independent reactions to deal with.
So what do you do with the other two reactions that we're claiming are not independent of the others?
Oh, you discard them. You don't need to deal with them. Basically,
really?
your system is your system is represented by those two reactions.
That is wild. Okay.
Yeah. Yeah, basically, you know, that's what it means, and that's why like it simplifies the problem that you're analyzing as we move forward. But the catch here is that you really need to make sure that all the chemical reactions in your system has been predefined before you go through that.
Right.
Like, you know, and we're going to be highlighting this in the upcoming slide. Like, for example, if you are dealing with natural gas is typically not 100% methane.
Yep.
It's gonna have propane and ethane. Yep. So if you would fail to be saying ethane and propane is in my equation, that's gonna be a big problem, because the thermodynamic like repercussions and consequences of saying that is going to be like significant. So, and this is literally what we were speaking about. If we are dealing with reforming reactions and you are dealing with like natural gas, the priority at any pressure and temperature over the steam methane reforming catalyst is going to be the heaviest go first. So as you see here, this is your propane. This has been like a specific natural gas composition that goes into your reforming section at any pressure and temperature. For the reforming, you are gonna find out like the propane is almost exclusively gone first. Then you are going to find that ethane is gonna be following, and then you start be like dealing with methane. So if you have the heavy goes first, and it's pretty simple because it's way easier to break bigger molecules than reform methane or the smaller molecule.
That makes sense. Yeah.
That's what it means.
Yeah.
So this is what the chemical equilibrium means in this case. And basically the chemical equilibrium is not like what I just put on paper. It's literally what my feedstock is. And this is one of the biggest errors some engineers actually do in industry.
Can you elaborate on that a little bit further? What do you mean by that? The biggest error that they make?
Oh, well, what it means is like when they are like trying to be like simulating a given steam methane reforming in a given industry to make hydrogen, for example.
Right. Yeah.
They will assume basically like the feedstock is methane,
right,
100%, for example.
Right.
And it's just proceeding. The problem with this is the following. If you fail to be defining the methane, like the other components of the natural gas, or you fail to define their chemical entity as like the chemical reaction proceeds, you are going to be having a deviation in the chemical, like, you know, when you are trying to characterize how the catalyst is effective, you are going to be either overestimate or underestimate what's going on. Because at the end of the day, in steam methane reforming, you're always trying to characterize how your catalyst approached the equilibrium.
Yeah.
So if you did not predefine the equilibrium correctly, you are going to be going in the wrong direction.
That's a good point. That makes sense. Yeah.
Yeah. And another part, like, also like to avoid errors in the future, like whenever people, like for example in methanol industry, they will try to be having a pre-reforming upstream of the steam reformer. And basically what it does is just like a little booster for chemical reaction to shift some of the duty upstream of that, utilizing a heat from the convection bank, for example. So if I have a lot of heavies in my feedstock, I will end up basically underestimating the methane conversion. And it might be producing errors downstream in the steam reformer itself. So again, that's where this becomes super critical.
That's an interesting, yeah. See, and a lot of, and it's funny, right? Because most people wouldn't be aware. Our industries are very different. So a lot of these topics aren't really, I hadn't thought about them in so long. You're making some very excellent points. Yep. Especially around the criticality of
And this is applicable to anything. I mean, like, if you are in you know, in a biological process, or like really like the type of feedstock and the composition of feedstock generally will impact how the thermodynamic equilibrium of the chemical reaction is going to look like.
Right.
Because we're dealing with mixtures of reactions.
Right.
Like, when we have methane, when I write it on a piece of paper, methane going to hydrogen, carbon dioxide, and carbon monoxide, it's way easier versus like when I have like, you know, ethane, propane, butane, and hexane as part of like the lights, the heaviest of like natural gas. Yep.
Right.
And yes, they are significant. That's the point. It's like, especially ethane, because ethane is the second biggest thing after methane. It can be like somewhere between 5 to 8%, and it's a really significant thing.
That's substantial.
Oh yeah, yep. Nobody's gonna give you methane 100% unless like it's really super expensive. So now, like, going beyond, like, now moving beyond the feedstock, the critical components for the steam methane reforming are pretty much 3 important factors: the reforming temperature, steam to copper ratio, reforming pressure. So what is the steam to copper ratio? Steam to copper ratio is basically the molar ratio of water to the number of carbon flowing to the reformer. For methane, the carbon is going to be 1. So basically for methane, the molar ratio of methane to carbon is going to be 1 to 1. So steam to copper ratio is going to be as you see there. But again, reflecting on what we mentioned, steam to copper ratio, if we go to ethane and propane, it's going to be like, you know, it's going to be way worse, because it's going to be like half and third and fourth as you go down there. And that means if you want to make sure that to avoid like the carbon formation, which we are not going to be highlighting in our episode today, you have to stay above steam to copper ratio of 2.5.
That's a really good point.
The problem is, if you don't know the composition and you're dealing with your natural gas as a methane, and you'll be like saying I'm above 2.5, but like you have propane and ethane there, that's where the trouble happens.
Yep, that's a really good point.
Yeah, so that's like, you know, it's basically the consequences I was telling you about earlier. These are all consequences of how accurate you need to define everything beforehand. So the great thing about this is the reforming reaction, as you know, it produces like hydrogen, carbon monoxide, and carbon dioxide. So it favors going from methane and steam to the product side at lower pressures. That's why, like, you know, the lower the pressure, the higher the methane conversion. Of course, the higher the steam to methane carbon ratio, or higher the steam to carbon ratio, the higher the conversion as well. because you are increasing the concentration of your reactant pretty much there, which is the steam.
Right.
And of course, that also goes for kinetics. So it's that's another thing. We're not related to this here, but as well, the partial pressure of steam would basically speed up your chemical reaction. When it comes to the reforming temperature, I mean, this is a deeply endothermic reaction, as we highlighted before in our previous episodes. And because it's around 246 kilojoule per mole of methane, you know, the beauty of endothermic reactions is that higher temperatures favors both kinetics and thermodynamics. And as you see here, the higher the temperature, the higher these methane
You're pushing the reaction forward. Yep.
So that's the great thing, and that's why like the steam reformers are gigantic furnaces for that specific reason. It's really cool. Because and of course, like another thing that to highlight here, why we're using a furnace, why we're not like using a steam reactor or something, and it's pretty much obvious in the temperature that we're dealing with. Temperatures that we're dealing with is super high, that can only be provided by combustion reactions, which basically an extension of what we have discussed last episode for the combustion reaction itself. So the last but not least is basically how like the carbon monoxide and carbon dioxide yield are being impacted by the steam to carbon ratio, and that's where we can show the three-dimensional picture of steam to carbon ratio, reforming pressure, temperature impact on the distribution of carbon monoxide yield, carbon dioxide yield versus the methane conversion. So that chart that we have here, that's three Y's correlated to each other. Those are not like X's. We're just like trying to show how like each of these products are distributed as you vary the pressure, steam to carbon ratio, and temperature. And of course, below there, you can see like, you know, based on the inlet temperature to the reformer, to the steam reformer, and the methane conversion, you can predict the heat duty that has been provided to there. So what does this means? It's like if you know how much energy you're burning and your temperature to the reformer, you can predict the methane conversion, and you can basically know how good your catalyst is. The second part is if you have the methane conversion, like let's say you have already an online analyzer at the exit of the reformer. Now, knowing that along with the reformer inlet temperature, you would be able to deduce how much energy the reforming is using, and you can say how efficient based on theoretical versus actual it is.
Right. That's really cool.
Yep, that's one of like, you know, the greatest things about like, you know, having this thermodynamics analysis for different reactions. It basically gives you this perspective in so many ways of how to gauge the efficiency of your system.
Hey, take a guess how many times I've seen that graph in my life.
I would assume 0.
It was once, it was today.
Oh, okay. I'm glad, like, yeah, I'm glad to hear
it's useful,
that.
right? Because, like, I mean, we've talked about it. Most of the time when I've been asked to run a process, I have a procedure and I have the steps that they follow. And like we've talked about, no heat material balances. I don't have equipment specifications. I don't really know, you know what I'm saying? I don't know what the most efficient pathway for my process is. So I don't know how close I am to whatever that optimum is or how far away. You know what I'm saying? And we get so used to as engineers operating on so little information, it just becomes commonplace.
And
it's just like your work with ammonia and your work with the polymers, like, unless you really know what your ideal process looks like, you don't really know what kind of improvements are at your disposal. You're just guessing.
Absolutely.
And you might guess wrong.
Yep. Absolutely. And of course, like, I can't even stress enough, like, if the thermodynamics is not even in that picture, that's like basically, you know.
Right.
So there's always going to be, like, it's a challenging in so many industries.
Yeah,
like,
yeah, absolutely.
You know, either like it's absent or a little bit obsolete. Like, you know, you would find like definitions like, here is my equilibrium mixture.
Right.
I mean, how does this going to be useful for you? I mean, if you have a different if you have a feedstock that's different from mine,
hey,
this whole thing wouldn't have any meaning. Yep. So yep. And that's how, by the way, like, you know, when you have like a reactor, for example, you can actually be able to basically characterize how it is, how much energy it's using, how much, you know, if there is anything going on, if there is heat losses, like, you know, to atmosphere or to ambient conditions, you don't have enough insulations. There's so many things that will be coming out of that because you'll be able to pivot against a reference.
And speaking of that, I know we're getting kind of long on time, but there are two processes that I'm thinking about right now off the top of my head where we actually use the heat demand of the process to tell us whether or not the reaction was proceeding effectively or if the catalyst we were using was beginning to die, right? And we didn't, and it, you know, it makes sense. We didn't really have like any quantitative definition for what was good and what was bad. It was just a lot of tribal knowledge, right? And so it's really cool to think about the fact that this stuff is out there in industry, but in most cases, you don't have this very technical viewpoint for things. It's just kind of,
absolutely. Like,
right, yeah.
Yeah, to reflect literally about what you just mentioned, like one of the concepts in the steam methane reforming is called approach to equilibrium.
Right.
And basically, that's what it means. Like at a given temperature, you would already know from thermodynamics how much methane should be converted.
That's wild.
And you know, given you know, given the feedstock and given the temperature and steam to methane, you know, carbon ratio, you'll be able to know what's supposed to be at equilibrium. The methane should be left there. But in reality,
that is really
the catalyst
useful.
decay. You know, the catalyst decays. You know,
right.
And pretty much like, you know, the catalyst, which basically the activation energy for the catalyst. You know, as it deteriorates, it means I'm gonna need like to pump more heat, more temperatures, to get the same conversion previously.
Right.
And that approach, this is the approach to equilibrium, meaning what is the actual temperature versus the theoretical temperature, and that basically the characterization that you have around the catalyst itself.
That's really cool.
Yeah. So just like wanted to add to what you just mentioned earlier. So, with that being said, just like to summarize what we have talked about today, we highlighted the matrix application in deducing the set of independent chemical reactions. And by the way, that same matrix operations, irrespective of if you are dealing with thermodynamics or you're dealing with kinetics, with different networking that's taking place on its surface of a catalyst, is the same concept. So if you are assuming there's so many kind of like pathways on the surface of the catalyst, you need to do the same kind of matrix operation because you cannot deal with all of them as independent. Just wanted to highlight that. The second part is we highlighted the matrix application to the steam methane reforming reactions. The last but not least, the industrial approach to steam methane reforming chemical equilibrium. So with that being said, that would be like on my end, would be like the last thing, and I hope like this has been very productive for our audience. And please, like, if you have anything on your mind, please reach out to us by email or on YouTube or even on LinkedIn with your comments, suggestions, or questions. That's it for me. Thank you.
Yeah, so just kind of pick up on what he said. This is a passion project for us. We really do hope it's valuable. The topics we've selected are just kind of topics that we're familiar with just because of what we've had to work on and what we've done. But obviously we have no issues branch out into something other. If there's something in particular that you'd be interested in hearing about or seeing or delving into further, I can't sit here and say that we're going to be the most familiar, but we don't have any problem addressing that, right? Hopefully you enjoyed this video. If you did, please like, leave a review, leave a comment, subscribe. And then if you have any questions or as I said, maybe you want to see something different, you can always send an email to sciencemadesimple@outlook.com. We are really interested in that feedback, and so we'd really like to hear from you and kind of get your thoughts on what we presented today. And that's all I got. Signing off.